Section 6, Reductive Amination, not to be confused with cartoon animation. So an amination reaction, installs the amine group. And this is a very powerful synthetic method to prepare primary, secondary, or tertiary amines in a very selective and controlled manner. Now, there are two things we need to remember from our previous course material, and that's to recall that ketones and aldehydes can react with ammonia, primary amines, for example, to give you imines, okay, imines. And the other thing to recall is that aldehydes and ketones can be reduced in the presence of sodium borohydride and methanol to give you secondary or primary alcohols. So, what is this reductive amination and what is it all about? Here's an overview of the chemical reaction. If you take a ketone and you treat this with your amine of choice, let's say, for example, ammonia, okay, with a drop of acetic acid catalyst. Now, this will make the imine, remember. Then, if you treat this with sodium cyanoborohydride, this will make your amine. Okay? So first, what is sodium cyanoborohydride? Okay? It's NaBH3Cn. That's how, the order of the elements that we have in there. And this is nothing other than a hydride reducing agent. So H is connected to boron, 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 and then we have a cyano group here, or a nitrile, or a cyanide, okay? So this is the Lewis structure for sodium cyanoborohydride. Now this is related to sodium borohydride. Okay, sodium borohydride is NaBH4. Let me write that in there. NaBH4. So that's sodium ion and boron with, 4 hydrogens here and a -1 formal charge on the boron. Okay. Now, the cyano group is an electron withdrawing group. Okay. And it stabilizes the negative charge on boron, and it makes the hydride less nucleophilic and very selective, okay? So this stabilizes the negative charge, and the hydride, remember H- is hydride, is very selective. It's less nucleophilic, and it's not going to just attack everything in the molecule, okay? So, this has all been worked out in the past, but this reagent right here is a source of hydride. This reagent right here is a source of hydride. So the mechanism is exactly like we saw with aldehydes and ketones, okay? Now, if you have a ketone, let's just do something really, really simple here. Acetone, okay? And we are to treat this with ammonia, okay? Catalytic H+, and sodium cyanoborohydride, okay? Now, there's no step 1 and step 2 here. Sodium cyanoborohydride is such a mild reducing agent. It can be mixed with the ammonia, even with a bit of acid, and it won't just kill the reagent right away, okay? So that's the cool thing about the sodium cyanoborohydride. Now, if we do this reaction, we will get a primary amine, okay? So remember, we're classifying this as a primary amine because the nitrogen is attached to 1 carbon. So we call this a primary amine. If we take acetone once again, and we treat this with, methylamine. Let me really be clear in showing the bonds to the hydrogens so we can really understand this a little better. Down below the arrow, okay, so we have H+ catalyst still, we have sodium cyanoborohydride, okay? And we're going to make a molecule that now has a nitrogen with a methyl group, okay, a methyl group, okay? And there will be a hydrogen here. There's still a lone pair. Remember, nitrogen normally is happy with 3 bonds. So this right here is called a secondary amine. And it's called a secondary amine because the nitrogen is connected to 2 carbons. It's connected to a methyl carbon and then the isopropyl carbon. So this is called secondary amine, okay? And you guessed it, if we take a ketone like acetone and we treat this with dimethylamine, with acid catalyst and sodium cyanoborohydride, we will be able to create a tertiary amine. So we got the methyl group attached to the nitrogen, methyl group attached to the nitrogen, and an isopropyl group attached to the nitrogen. So since the nitrogen is bonded to 3 carbons, we call this a tertiary amine. Okay? So these are called amination reactions, and it's a great, very overall synthetically useful reaction. Okay? So let me go ahead and do some practice problems since there's nothing more to talk about this, okay? Okay, here we are, question 14, and we want to use what I call the disconnection approach to synthesize the, these following amines, okay? Now they're complicated, okay? So what you can do is break molecule A down into 2 parts, okay? So first, realize that you're making a nitrogen-carbon bond in this reaction. You're making a nitrogen bond to the carbon of a carbonyl containing component, okay? So this right here is going to have to be a carbonyl, okay? So this could possibly come from the amine on the left and the carbonyl on the right. Don't forget to include that carbon that that blue arrow is pointing to. And in this case, if we change that to a carbonyl, that's going to be an aldehyde. Okay? Now, the other way of making this is the carbon on the left. Okay? Another way of making this is the carbon on the left. If we do this, we want to make a carbonyl on the left carbon. I'm sorry, I didn't even draw the bond correctly. So let me delete this whole thing. So here's the bond we're talking about. The nitrogen-carbon bond is the one we want to create. So this would be my amine on the right-hand side. So let me jot that down here. I'm just going to flip it around a little bit. Okay. Now, we want to draw the other component, which is going to be a carbonyl-containing component, like an aldehyde or a ketone. If I make a carbonyl on that arrow to carbon, that's going to be an aldehyde as well, but with a 5-membered ring. Okay, 5-membered ring. Okay, so how do we draw these synthetic reactions? One possibility is to, start with the aldehyde. So we want to draw the aldehyde here. Okay, draw an arrow. Above the arrow, I would write this nice little amine that we figured out here. Okay, make sure you put H plus in there, which is a catalyst, and then write out the alphabet letter soup for sodium cyanoborohydride, and that's going to give you your molecule A there. The other way that we could synthesize this molecule is by starting with the other aldehyde, which is a 5-membered ring, okay? Cyclopentane carbaldehyde, okay? In the presence of this amine, which is the 6-membered ring, okay? Put your comma, H plus, and then write out your alphabet letters for your reagent, okay? And that'll also get you product A. So let me make a new slide and we'll keep working on these problems. In part B, we have a variety of choices to use here, okay? Now, since we have 3 carbon-nitrogen bonds, we can choose to break any one of those 3. Now, if we break the methyl group, that's definitely going to be a unique choice. That's one answer. If we break the carbon on the left, that's the same as breaking the carbon on the right, so that's another answer, okay? So let me erase this, and we'll consider breaking the carbon that's on the methyl group, okay? So if we break this bond right here, this is going to be the amine. So let me sketch out what that's going to be. Okay, this would be called dipropylamine. And then what about this carbon up here? What do I do about that? I change that into a carbonyl, okay? The carbonyl that has just 2 hydrogens attached to it is called formaldehyde. Okay, so that would be one possible combination, all right? Let me delete my retrosynthetic analysis, and we'll scribble some stuff on this here to think about what would happen if I broke this bond, okay? I would want to start with this amine right here, okay? We would call that methylpropylamine, and then the carbonyl containing component would be here. That's going to be an aldehyde with 3 carbons. Okay, so let's write down the synthesis that would be required for those. Route 1 would be to take formaldehyde, add this nice little dipropylamine, H+, NaBH3Cn, and that will get molecule B. The second route would be to take propanal, methylpropylamine, don't forget your H+ catalyst, and it doesn't need to be step 1 and step 2, right? We said that these could be co-mixed together. So NaBH3Cn, that's going to form molecule B. All right, I hope you're getting the idea of this, okay? Now let's do C, D, and E, which contain rings. All right, part C looks kind of complicated because it's in a ring, but we're just going to go ahead and do this one anyway. So we want to propose 2 possible syntheses for this, and that's great because this molecule has 2 carbons, you know, one in the ring on the left that doesn't have the methyl group, and one on the ring kind of down to the bottom, which does have a methyl group. So there's 2 possible disconnects. We first want to choose maybe the one on the top here. Okay, so we're going to consider breaking this bond right here. Now, what do we do with the carbon up there? We change that into a carbonyl. Okay, so we add a double bond O, and we make sure we indicate the aldehyde H if it's an aldehyde. Now, the rest of this molecule is just going to be an amine, which includes all of that component. Okay, so it's going to be amine on one carbon and an aldehyde on the other carbon. So one possibility would be, here's my aldehyde, okay, and that's all wrapped around and connected to my amine, okay. Remember, nitrogen always has 3 bonds, so I need to write NH2 there. All right, that would be one possibility. A second possibility, let me erase all of my retrosynthetic analysis here, is to break this bond right here. If I do that, again, I want to make that an NH2 group, and then I want to add a carbonyl to that carbon. So it's going to be a ketone, isn't it? And remember that all of these carbons are bonded to one another. It's not 2 separate molecules. So we have the amine, which is here, and then we have our ketone, which is here. Okay. So how's the synthesis going to look for this? Possibility 1 is that we're going to take this molecule, and you can draw this molecule any way you want. Just make sure that it's 5-aminohexanal, okay? And so what we'll do is we're not going to add an amine to this because the amine is already present in the molecule. So we're just going to add H+ for a catalyst, and then we'll add NaBH3Cn, and that'll make molecule C. Possibility 2 is to take this ketone, this amino ketone, and same kind of thing, H plus, NABH3CN, and that's going to give you molecule C. All right? You get the idea for the rings now, I hope. Let's do some others. Problem D here. And this molecule is symmetric down the middle, okay? So we could break this carbon here from the nitrogen, which would be the same as doing that for the carbon on the right. So that's one possibility. And the other possibility is to break that carbon, okay? So these are the two disconnections we can possibly do for this molecule, okay? Because the nitrogen is part of the ring, we see that it's going to be one single molecule, okay? So let's first examine this. Again, we're going to change that to the amine, so we're going to add an H. And this one here, we're going to change to a carbonyl. So our first molecule is going to be an aldehyde up on top. And our other fragment, I'm having trouble counting to 6 here, is going to be part of this 6-membered ring. And there's going to be an NH. Okay, so this is an aminoaldehyde. The other possibility, let me erase all of my retrosynthetic analysis here, is going to be if we break this bond right here. So again, we want to change that to an amine by adding an H, and we want to change that to a ketone, in this case, by adding a C double bond O. So that possibility is going to be that, all right? It's kind of hard to draw that, all right? So let's go ahead and show the synthetic reactions that we could do for this type of molecule. It's always a good idea to count carbons afterwards and make sure there aren't any blunders here. Okay, that looks good. And so once again, since the aldehyde and ketone are within the same molecule, we don't need to add an aldehyde, we don't need to add an amine, it's all present. But we do need to add the H plus catalyst to form the intramolecular imine, iminium ion technically in this case, and then we add NABH3CN, and that's going to give me molecule D. The other possibility, I have no better way to draw this, is going to be my very strange looking molecule there. And same reagents, H plus is the catalyst, NABH3CN is going to give me molecule D. All right? Let's do part E now. Okay, for part E, we have 3 different carbons. This molecule is not symmetrical in any way. We have carbon 1, carbon 2, and carbon 3. This is a tertiary amine, so we could disconnect it any which way it seems that's possible, okay? So I'm going to show you why one of those actually does not work. So let's first do carbon 3. Okay? If I break this bond here, remember the trend, I add an H to this amine to get it to be an amine, and then I add a C double bond O to this carbon to make it a ketone, in this case just simple acetone. So this indeed is 2 different molecules, okay? We have this amine with a couple of methyl groups here, and we have a ketone known as acetone, okay? That seems like a reasonable disconnection, okay? Let me erase the retrosynthetic analysis here, and let's try to break it around this carbon here. So here we would add a hydrogen, and then on this carbon we would add a C double bond O. So what I would get there is my amine. That looks fine. There's a problem here, right? Because we know carbon can't have 5 bonds. So this sort of disconnection is not possible. If you have a quaternary center next to an amine, you can't make that by reductive amination, okay? So we're not going to draw that, okay? That's just embarrassing even to consider here on the YouTube video. So what we will do is, rather than disconnect that bond, disconnect here, okay? So up here, we're going to add a C double bond O, which is an aldehyde, and here we'll make that an amine, okay? So what do we get? An aldehyde up top, and your isopropylamine here, okay? So what do we do? Let's show the synthesis here. I'll erase this silly consideration here, okay? And let's indicate what the synthetic reactions would be. So here we are. We have our ketone, which is known as acetone, and we want to add our amine. H plus catalyst, and again, you don't need a step 1, NaBH3CN, and that's going to give you molecule E. The second possibility is to take this aminoaldehyde, it's pretty sterically hindered, but anyways, we do the same steps. We would add H plus catalyst. Now we don't need to add an amine or an aldehyde because it's internally present in the molecule, so it's just one single molecule. And NaBH3CN would be what you need to do to convert that to to molecule E. Okay. So that's pretty much it. I'm going to end the video here, and I hope this illustrates a little bit about the basics of reductive amination. Thanks for watching.